Let's now talk about implementing a feedforward network with GELU activations. Here, the feedforward network is a small neural network contained in the larger neural network, the LLM, and the GELU activations are nonlinear activation functions. So it's essentially a concept in deep learning where we have linear layers and nonlinear activation functions. So just before we go into these details in the grand scheme of things where we are, so our goal is still to implement the final GPT architecture that we want to train in the next chapter. However, the GPT architecture consists of multiple building blocks that we are working through sequentially here. So we already covered layer normalization. So first we coded this dummy architecture, then we covered layer normalization where we were coding this normalization layer that goes between other neural network layers. And now we are going to code the GELU activation that also goes between linear units or neural network layers. So why do we need nonlinear activations in the first place? I was just digging out an older figure from a university lecture I gave when I was a professor back in the day. So here, this is like a multi-layer perceptron architecture that consists of multiple layers. So we have the inputs, a first hidden layer and a second hidden layer, and then the output layer. And so this is a classic multi-layer perceptron that you may have seen in the context of deep learning. And what's not shown here are the nonlinear activation functions. So I'll scroll a bit down. So I had it usually as an exam lecture. What happens if we don't have the nonlinear activation functions? Just briefly, the goal here, also in the grand scheme of things of the large language model, is to extract features from the input data, and the features go through the neural network layers. And at the end of the day, we want to generate outputs. And for the feature extraction, we want the network to learn something useful that helps the network to generate the correct output. Now, ideally, this is a toy problem, but if we have something like this, and this is a classification task, has nothing to do with neural networks, with LLMs, but for illustration purposes, think of this as a challenging classification problem where the network should detect whether something is a square or a circle based on some numeric input. And ideally, the network would learn something like this, like a decision boundary where it can separate these squares from these axes. So they look a bit different from here. But the goal is essentially separating two types of inputs here. And if we don't have these nonlinear activation functions, what happens is essentially that we only have linear layers, and the combination of linear layers is a linear function too. So the network will only learn linear functions. And then what it means is the network will never really learn to extract useful information from the input. So it's kind of like limiting the network severely if we don't have nonlinear activation functions. And so nonlinear activation functions, there are a whole bunch of them. So the sigmoid one is a classic one. There's a 10H function, hard 10H, and I think I even have like a fun figure somewhere here. There was even like this meme where someone was like mapping nonlinear activation functions to dance moves and so forth. And so there's a whole bunch of nonlinear activation functions. And the one that we are going to talk about today is not even on here yet. It's called GELU, which is somewhat related to ReLU, but also not quite. And we will see in this video how things are related. So going back to some of the figures here, again, where the nonlinear activation function fits in is if we have a neural network and we have multiple linear layers, the GELU function sits between linear layers. So it's usually a linear layer followed by a nonlinear activation function. You can also see that here, where we have a linear layer and then the nonlinear activation function. And this whole thing here, a feedforward module, is the module that is later coded in the transformer block. So we haven't talked about the transformer block yet. We will talk about it later, but I can actually maybe already show you the figure so it's a bit more clear where things fit into the grand scheme of things. So this transformer block is part of the LLM, and this gets repeated a number of times. And inside this transformer block, there is the so-called feedforward module. And part of the feedforward module is this setup where we have a linear layer, a nonlinear activation function, and a linear layer. And in this video, we are going to take a look at what this GELU activation function is. So yeah, a lot of background information. I hope this is not too confusing. Essentially, we're just coding a small little function inside this whole thing. And the GELU function goes back to a paper called Gaussian error linear units. And here in this paper, they proposed a function that is essentially a bit better than the ReLU for optimization purposes and so forth. And one more thing here. So the ReLU function, there's actually a nice figure here how it relates to the GELU function. So the ReLU function is a function that is maybe the simplest nonlinear activation function. What it is doing is if the negative, so if the inputs here on the x-axis, if they are negative, they are thresholded to 0. So the y-axis is the output, the x-axis are the inputs. If the inputs are negative or below 0, the output here is 0. Otherwise, it will maintain the input. So if the input is 1, the output is 1. If the input is 2, the output is 2, and so forth. And the GELU is, it's very similar. You can see it's slightly different. It has some beneficial mathematical properties for normalization or for optimization during the training. So if you're interested, you can read through this paper, but it's not super essential. You can think of it just as a nonlinear activation function, one of the many nonlinear activation functions. You can actually train also the LLM with other types of nonlinear activation functions. It's just a choice that the original developers of the GPT model made. And in fact, later LLMs, for example, the Llama models, they use something called a SWIGLU activation function, which is a gated unit with, I think, SILU activation function. So, it's just like a choice some people make. So it's not super crucial. The only thing that is crucial is that we use a nonlinear activation function. Which one? Well, it depends. Some might sometimes work better than others, but I wouldn't get too, too serious about which type to use here. One thing about the GELU activation function is that it comes actually in two flavors. So this is the mathematical formulation of the GELU function, but the original GPT model, it was implemented in TensorFlow, and they used this approximation here, so this mathematical formula. And I don't know 100% because I haven't talked to the authors of the original GPT architecture, but I can assume, or I would assume that this is probably due to efficiency reasons that they use this approximation. So it's, approximately the same, but it's approximated, it is maybe a bit faster. Again, it doesn't really matter in the grand scheme of things, but because we want to mimic the original GPT architecture, we are also going to implement this version here in PyTorch. So this was like a lot of build up, a lot of background information. So let's actually get to the code. And I think once you see the code, you will feel like, okay, this is actually much simpler than you thought compared to the paper and everything. So here, what I copy and pasted here is my re-implementation of the Approximate GELU function, and you can see it's a very similar module. It has a forward method and it receives some input, and then it applies this formula. It multiplies the input by 0.5 and then multiplies it by 1 plus this 10h and so forth. And so this is just a mathematical approximation of the GELU function as described in that paper. And if we use that, let me just also copy that code here. We can visualize it. I'm using Matplotlib here. And I'm going to apply to some sample data in the range between -3 and 3. So the input, going back to the paper, I'm just testing it between -3 and 3. That's what I'm doing here. And I'm also, for completeness, I'm comparing it to the ReLU function in PyTorch. And here it's just plotting code. So let's see how that looks like. So maybe I should interrupt this. I think, of course, I forgot to execute this code cell. I think it should be pretty fast. I think my computer is still suffering a bit because in the previous video I executed this large matrix multiplication, so I should probably restart it at some point. But yeah, here we can see the figure. So we have -3 to 3 here as the input, and then you can see the output here. And yeah, it is ultimately same idea as the ReLU function, except it's a bit smoother here, which has nicer properties during optimization when we compute the gradients. Yeah, and then just to go back to the chapter here. So I talked about this little unit that we will need actually in an upcoming section when we implement the transformer block. And so we are going to implement the code for this. I think it was further up here. Yeah, so we're going to implement this one. So let's do this, and this will be something we are going to use later. So what is happening here? So we have a feedforward module, and we have a sequential here, which means it will, in the forward method, it will execute everything that is inside the sequential in a sequential fashion. We have a linear layer. So this goes from the embedding dimension. And if we go back up here, the embedding dimension was 768. So it goes from 768 to 4 times 768. So we have 768 to 4 times 768. And so this should be something with, I think it's 3,100, but let me just calculate it, 3,072. So it's 3,072. Let's just put it here. And then it goes from 3,072 back to 768 here. So it is essentially a network that is the opposite shape of an hourglass, where we go, instead of an hourglass, we go from large to small to large. Here we go from small to large to small. I do think I have a figure here. Yeah, so here you can think of it as this. We have the small embedding dimension. We make it 4 times larger, and then we make it small again. Why do we do that? So this is, it's like a trick almost in deep neural networks, where this adds a lot of parameters, and these parameters learn to extract some information from the inputs. It's essentially, you can think of it as massaging the input to, get to extract information for it, that then during the optimization, when the weight matrices are optimized, help the network learn to extract relevant information and do something useful with that. And in this case, in the case of LLMs, it's correctly generating the next word in the text or input data. And this is our mini neural network that we are going to use in chapter 5, when in the transformer block, but then also in the LLM that we are going to train in chapter 5. We can initialize it. So let's go here and do FFN, and then let's do feed forward. Oops. Maybe execute this, of course. It's a running gag by now, I think. So we can use so we have the CFG, which stands for configuration, which we have defined up here. So this is our configuration here. So let's just use that and put it in here. And that is our mini neural network. And then we can try it on some sample data. So we can, just for simplicity, create some random data again. So let's do 2 by 3 by 768. So a batch of 2 input samples. Each one has 3 tokens. And then each token embedding is 768 dimensional. It's just a sample. Later, we will work with real data. But yeah, just to show you what happens. So here we get the same output shape, and that is because we have this input dimension that is also generated here. So intermediately, there is a larger value, or 4 times as large, the 3000, but what we get out is still 768 because we map from here to larger and then from larger back again. And why is it 4 times? So this is again a hyperparameter. So it could be as well be, it could be 2, it could be 8, it could be 1, it could be anything. This is something the original authors of the GPT paper chose. And again, like I mentioned before, we want to mimic the original GPT architecture. And Also, why I'm so hung up on the GPT architecture, why we want to mimic it exactly, is that later in chapter 5, we will download the available weights that OpenAI shared on their website, and then we will load that into our code here. And so there are weight parameters. So if I go here, and then let's say layers, right? So this one, you can see there are these weight parameters. So when we have this one, this is the first linear layer, and then we have the weights here. And these are currently random weights, but later we will train them and we will also load the original OpenAI weights. And we have to have the exact same dimension that they have if we want to load their weights into our model. So we have to match these things exactly so that the weights are compatible. And that's why I'm trying to really make sure everything else is the same. We use the same hyperparameter here. We use the same approximation here that they used in TensorFlow and so forth. And yeah, so that's why it's so important for me to match these things. And yeah, in this section, now you saw the GELU function. In the next video, we will tackle another building block of the LLM architecture.
Get this book at Manning.com.